All right, we're going to be looking at the beginning of chapter 5 for chemistry 1211. And we're going to be talking now about molecular shape. And we've been drawing Lewis structures, but the actual shape of the molecule is not always the way that we draw it. Shape is really important in chemistry because molecules interact with other molecules in biology, especially with something called an active site. And you may know this if you were taking a biology class where like an enzyme has an active site and it has a certain shape of the molecule. For example, the molecule that makes up the taste of spearmint, these are caraway seeds and bread, all have a similar shape, but there's just one small little change in that shape that makes the difference in something like these caraway seeds for the bread and then the spearmint here. So a little bit of change in shape can actually change how the molecule behaves and its properties. So we're going to start with Lewis structures, and then we're going to build into shapes. You'll see me use in class, I'll pull up a simulation for you that uses ball and stick models. You can actually buy yourself like a model kit that has this in order to see these real bond angles. And so what I want to show you here is that while I may draw the Lewis structure in a straight line, for carbon dioxide, for example, the ball and stick model does show that this molecule would be in a straight line. It would have a 180-degree angle. But for methane, I might draw it with these 90-degree angles, but the real angle is going to be 109.5 because this is a 3D shape, pops out into space. And we'll explore that a little bit more in class where I can break down the simulation with you because that'll help. But just know that because you draw it in a certain shape on paper doesn't mean that that's going to be the exact bond angles. We get bond angles from looking at the actual shape it's going to be in, not just our shape of our Lewis structure. And so where do we get this from? We get this from valence shell electron pair repulsion theory. I'm going to call this VSEPR. Electrons have negative charges, and so they repel each other. The VSEPR theory predicts that the electrons are going to be arranged around the central atom in a way that minimizes that repulsion. And so if we have two balloons, let's say, for example, the balloons are the areas of electrons, like orbitals, for example. And so the electrons are going to be as far apart as they possibly can. And you can see as we add more balloons, we get a little more complicated with our shapes. We're looking at this thing Sn. This is steric number. And steric number is the number of electron areas around the center atom. And as we increase our steric number, you can see we get a little bit more complicated with our shape. We're going to be talking about electron pair and molecular geometry. So electron pair or electron geometry is just looking at all the electron groups around the center atom. And so we look at the steric number. Steric number is the number of atoms that are bonded to the central atom, so the number of bonds, and the number of lone pairs in the central atom. And so remember that when we're counting the number of atoms bonded to the central atom, it doesn't matter if it's a single bond, double bond, triple bond. It all counts as one area of electrons. And then we will take these number of different electron groups and kind of spread them out as far as we can get in a 3D structure. Electron pair geometry just looks at groups of electrons. Molecular geometry only looks at atoms in that molecule or polyatomic ion to describe the 3D arrangement. So it doesn't look really at lone pairs. It looks at the result of what lone pairs do, but it doesn't actually count them because we can't actually see those. We only look at the atoms. So let's look at molecular geometry of the central atom if it has no lone pairs. If we have no lone pair on the central, you would have SN2 would be linear. SN3 is trigonal planar. We can see that it's a triangle because there are three things bonded to the center and it's flat. So this image is trying to show you that it's flat. Again, we're going to play around with this in class with a simulation. Simulation is also on D2L if you wanted to check it out on your own. Tetrahedral, which is actually just like a pyramid with a flag on the top. Trigonal bipyramidal, which is like two pyramids mirrored, stacked on top of each other. Again, we get that triangle kind of shape it's trying to show you there. And then octahedral. An octahedron is kind of like the thing that goes above a Sim's head. Or you can think about it as, I believe it's a D6. If you're into playing D&D. Or no, a D8. 1, 2, 3, 4. Yeah, 4 sides. So it's a D8. Some examples here would be these Lewis structures. So draw these Lewis structures and see how they look maybe a little bit different than what you're seeing in the models. So these are models of showing us these different molecular geometries. So this is what that trigonal bipyramidal actually looks like. You can kind of see how we might get a pyramid shape, and it's on top of each other. Then you have the octahedron here, which has essentially these four sides. So it's like a D8. If you ever have just looked up Dungeons and Dragons D8 dice, so it's a dice with 8 sides. So why don't you try drawing formaldehyde, H2CO, and then tell me what you think the molecular geometry would be. So as we go to draw H2CO, we're going to count up 2 hydrogens and 1 carbon and 1 oxygen. We're going to count up those valence electrons, and you should get a Lewis structure that looks something like this. Now we're going to think about how many electrons groups do we have around the center atom. Well, the double bond counts as 1, so that's 1 electron group, 2 electron groups, 3 electron groups. So the SN is 3, which means my electron geometry is trigonal planar. So let's think about drawing that. Trigonal planar, if we look at it, has an angle of 120 degrees between the bonds. So if we draw it in a way that shows that, we get something that looks a little more like this. So electron geometry is really looking at the shape of those electron groups, the shape of the orange highlights that I have here, the shape of those balloons, that if those were electrons. Then the molecular geometry would be, what if we took the balloons away and we only looked at the orientation of the atoms with each other? So what if I if I drew it in this right shape and then I went and erased those electron groups? We would see this triangle, and it's flat because there's no lone pairs in the center. So we would see that trigonal planar. So planar meaning flat. But still would see that 180 angle. So we'd only really be looking at the relationships. Think about like a ball and stick model. There. I don't recommend drawing it necessarily like that, like taking out the bonds, but that's essentially what molecular geometry is looking at, is only the relationship between the atoms, not the electron groups. These are going to be the same. Molecular geometry and electron geometry are the same anytime you have no lone pairs in the center. So no lone pairs on the center. Same electron geometry and molecular geometry. They both are trigonal planar. Now, if we have lone pairs in the center, which you know we do, it's going to change our molecular geometry. So electron geometry is going to be the same, just depending on the steric number, the SN, which is the number of electron groups around the center. So if we look at this ozone, we have 1, 2, 3 electron groups around the center. So that's where we get the SN of 3 of. So that's automatically trigonal planar because it's got an SN of 3. However, if we take away the electrons and we only look at the atoms, we get this bent shape. Because there's this lone pair up here we can't see pushing down on the bond, so it's bending it. So it's still going to have around a 120-degree angle, maybe a little bit less than 120 degrees, because those lone pairs push a little bit harder than the regular bonded electrons would. So molecular geometry would be bent. So we see the actual bond angle here is 117. You don't need to memorize the actual bond angles, just know that it's a little bit less than the normal bond angle. For an SN of 4, we have 3 different options. We have no lone pairs, would be tetrahedral. 1 lone pair is tetrahedral electron, but we call this trigonal pyramidal for the molecule. 2 lone pairs is tetrahedral for the electron geometry, and we call it bent for the molecular geometry. And you notice that the angle starts at 109.5, and it gets a little less and less the more we add lone pairs. You don't need to memorize the 107 and the 104. Just say less than 109.5. And then know that this one is a little bit less than that. So I like to say less than 109.5. It doesn't mean that it's like that much less. So obviously 104 is not that much less than 105, 109, but it's just less than the previous one. The more lone pairs you add, the smaller your bond angle is, because the lone pairs press against those bonds to press them together. If you have an SN of 5, here are all the ways in which you can have combinations of lone pairs versus bonds. And again, we're going to go over this in class, and with a simulation, it's going to help out a little bit more. And then here's SN of 6. You have a handout or 2 pages in your memorization list that are going to help you with this. So get that out as you do any sort of practice. So we are going to do practice with this. We're going to practice Lewis structures and also then add this on. So this is not like too much extra new stuff. It's really Lewis structures, but then just use that sheet. This content will maybe be on a quiz or homework, but it won't be on exam 2. So just get the Lewis structures down for exam 2, but you may see some shapes on quizzes and homeworks. And again, we're going to practice this a lot in class.